Good morning, friends. I feel today very happy and overwhelmed to be here in my course Aircraft Systems. And as of now, I am in question bank answer session and module of 5. And today's topic is flight control system. I will be discussing about module 5, flight control system of the aircraft. And this is my last lecture for this course. As you know, my name is Dr. Dwivedhi, professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. As of now, I have completed 65 lectures, and these lectures belongs to the aircraft systems. This aircraft systems course is divided into the 4 modules. The module 1 is related to the introduction to aircraft systems. In this introduction, all the aircraft systems are given in brief. Like, we have divided the aircraft systems into 4 groups. The first one is airframe or aerostructure system. The second one is vehicle system. Third one is avionic system. And the fourth one is a mission system. Once I have started the airframe system, in airframe system, we have basically 3 major components. This I can show you here in this. In this we have the first one is the wing, another is empennage, this part here, and third one is the fuselage system. So in the wing system, the total lift of the aircraft is produced by the help of the wing. Also, the wing carries the fuel, the engine, the landing gear, and so many other electrical and electronic parts are accommodated in the wing also. Most of the engines are fixed on the wing. The landing gears are also fixed. One is here and one is here. And one is at the fuselage below the pilot. So wings plays a very important role for the efficiency and the performance of the aircraft. And the design of the wing, we have to see how we can do it better way. Second one is the empennage. So this part, the behind part, it consists of the vertical tail or the vertical stabilizer, and then we have the here, as you can see here, we have the rudder here, we have the horizontal stabilizer and elevator, and also this tail part is also there. So this is called empennage. Once we talk about the fuselage will start the whole this tube part where the pilots, the passengers, the cargo, so many electronic equipments, hydraulic bay, and so many things, air conditioning system, all are accommodated inside this fuselage. The wing also is attached to the fuselage, and here we have a keelson. In the keelson, the whole attachment, it is toughest part of the aircraft is keelson. In keelson, all these wings, everything will come and join there. So this part is also on the fuselage itself. So fuselage is also very important. Next, we have discussed about aircraft vehicle system. In aircraft vehicle system, we can see that we have the flight control system, we have the propulsion system, we have the hydraulic system, we have the electrical system, we have the firefighting system, we have the anti-icing and de-icing system, we have the oil system, we have so many other systems are there, environmental control system. This is part of the aircraft vehicle system. Third one is avionic system. In this avionic system, we can divide into the 3 parts. One is the navigation system, another is the display system, and third one is the communication system. So navigation system means to direct the aircraft from one place to another. We should have some guidance. This navigation will provide the necessary direction to reach to the required place. Once we talk about the communication between pilot and the ATC to the pilot to the ground station to the pilot, and any other communication is also performed by the aircraft. Next is the display. So in the cockpit, we can see there are hundreds of equipments. These equipments has to be work, and this is nowadays by use of avionic, it has made very nice to see also, and all the parameters are very easily visible on the cockpit. So this is the avionic system, and the last one but not the least is mission system, and this mission system consists of the sensors, then we have the computational, and then we have the mission requirement. This is missions, and this all things weapons system. So mostly the fighter aircrafts of the military, Air Force and the Navy and Army, they are equipped with the mission avionic or the mission systems, which are very important. So these things were covered in module 1. In module 2, we have seen the aircraft electrical system, power generation, power production, then power control, safety, then conversion, different types of power, AC, DC. In AC, we have the constant frequency and the variable frequency, 115 volt DC 3-phase. If you talk about the DC, we have the 28 volt DC, then we have 270 volt DC. These 4 types of power generations are used in aircraft. Next, if you talk about the environmental control, refrigeration and air conditioning, cabin pressurization and all fall under the module 2. In module 3, we have seen the hydraulic system and the pneumatic systems, all operation of different types of hydraulic system, green, yellow and the green systems, and different pneumatic systems also we have seen. In module 4, we have seen the engines and the engine control system. We have seen the FADEC, we have seen the ECU, we have seen the flight control unit, fuel control unit, and so many other types of things we have seen in our module 4. Now, here I am the module 5, that is the flight control system. So, I will be discussing about this. In this topics and the CO mapping of this flight control system is a CO6, canard as flight control surfaces, primary and the secondary controls, mechanical control, fly-by-wire, and the actuators are in this part of this. So here we can see here that describe the principle of flight control, principles of flight control system. So the motion of an aircraft is defined in relation to the translational motion and the rotational motion around a fixed set of defined axis. I will be discussing just after this. Translation motion is that by which a vehicle travels from one point to another in space. Rotational motion relates to the motion of the aircraft around the 3 defined axes, pitch, roll and yaw. Nose up and the nose down with respect to the pitch axis OI, called the pitching axis. Nose side by side is with respect to the yaw axis, OZ, it is called the yawing. Then wing up or down with respect to the roll axis OX, called the rolling. Climb only in the pitch axis OI. Turn is around the roll and the yaw axis OX and the OI. Climbing or the descending, turning maneuvers involves all the 3 axes. So this we can see here that in this diagram that we have the, here this is the pitch axis from here to here. This is the longitudinal axis or the roll axis, and this is the yaw axis. So this rolling, if this wing, it is a left wing is going up and right is going down, it is a positive roll. If nose is going up, it is a positive pitch, and if nose is going towards the right here, it is a positive yaw. And this all things are happening with respect to this 3 axis. And this 3 axis, we can have the translational motion, we can have the rotational motion. Explain the secondary flight control. So we have seen that the primary flight controls are elevator, rudder and the ailerons. But we have something, it is called the secondary also. Sometimes we need to control by the secondary also. If sometimes primary not working, that time we have to use the secondary control. So high lift control is provided by a combination of flaperon and leading edge slats. The flaperons may be lowered during the landing approach to increase the wing camber and improve the aerodynamic characteristics of the wing. The leading edge slats are extended during combat to increase wing camber and lift. The penalty for using these high lift devices is increased drag, but the high level of thrust generated by a fighter aircraft usually minimizes this drawback. They extend air brake to 30 degrees, thereby quickly increasing the aircraft drag. The air brakes are deployed when the pilot needs to reduce speed quickly. Air brakes extended during the landing run to enhance the aerodynamic brake effect and reduce wheel brake wear. So this I am going to discuss slowly. So this high lift control is provided by combination of the flaperon, means flap and aileron, and the leading edge slats. The leading slats are on the wing leading edge, they are fixed. Flaperons may be lowered during the landing approach to increase the wing camber and improve the aerodynamic characteristics. So if you see here, this is the wing here. So during landing, this is called the slat. This slat is lowered. So from here, you have the wing camber is increased from here to here. And this is the flaps. This is the flap here. And this is the leading edge slat. So now if you see this much, your camber is increased. Okay. So this leading slats are extended during the combat to increase wing camber and the lift. So during the flight, if you want to, all of a sudden, you want to climb, you have to increase the slat. The penalty for using a high lift devices is increased drag, but the high level of thrust generated by a fighter aircraft usually minimizes this drawback. So there is a drawback for this because drag will be increased, but in a fighter aircraft, they have sufficient amount of engine power. That engine power is able to handle the high amount of drag. We also use the air brakes to 30 degrees, thereby quickly increasing the air drag. The air brakes are deployed when the pilot needs to reduce the speed quickly in the air. So these air brakes are used to reduce the speed in the air. Air brakes extend during the landing run to enhance the aerodynamic brake effect and the reduced wheel brake wear. Secondary flight controls are shown here. It is the slats are here. These are the slats. This you can see here. And these are the flaps. And these are the spoilers, and they are normally 30 degree. It is lifted. If you see here, we have the trim tabs, and these are shown in this diagram. Secondary flight controls, we have the different types of flight controls like Krieger flaps, hinge flap on the leading edge, plane flaps rotate on the simple hinge, split flap, upper and the lower surface are separated. The lower surface operates like a plane flap, but the upper surface stays immovable or moves only slightly. Fowler flaps slides backward before hinging downwards, thereby increasing both camber and chord, creating a larger wing surface, better turned for lower speed. Slotted flap, a slot or a gap between the flap and the wing enables high pressure air from below the wing to re-energize the boundary layer over the flap. This helps the airflow to stay attached to the flap, delaying the stall. Blown flap systems that blow engine air over the upper surface of the flap at certain angles to improve lift characteristics. Flow control system. Flaps are hinged surface on the trailing edge of the wing of a fixed wing aircraft. As flaps are extended, the stalling speed of the aircraft is reduced. Flaps are also used on the leading edge of the wing of some high-speed jet aircraft, where they may be called Kruger flap. Flaps increases the camber of the wing airfoil, thus raising the lift coefficient. This increase in lift coefficient allows the aircraft to generate a given amount of lift with a slower speed. Therefore, extending the flaps will reduce the stalling speed of the aircraft. They also increase drag, which helps to slow the aircraft. So now demonstrate the high lift devices used on airplane. So what are the high lift devices which are used on airplane? This I am going to discuss here. So the high lift devices are the slats. So slats are also known as leading edge devices, are extensions to the front of the wing for a lift augmentation and are intended to reduce the stalling speed by altering the airflow over the wing. Slats may be fixed or the retractable. Fixed slats give excellent slow speed and STOL capability, but compromise higher speed performance. Retractable slats, as seen on the most airline, provide reduced stalling speed for takeoff and landing, but are retracted for cruising. Leading edge extensions. So this you can see here that these are the slat here. These are the slat. This you can see here. These are the slats, and here also these are the slats. So these are the high lift devices. When want aircraft to get more lift, it is extended. Next is the leading edge extension. It is called LEX. Leading edge extension or LEX, also referred as a leading edge root extension or LERX, or stacks or chines or fillets added to the front of a modern fighter aircraft wing in order to provide usable airflow at a high angle of attack. They are typically roughly triangular in shape, running from the leading edge of the wing root to the point near the cockpit along the fuselage. They tend to be fairly small in span, extending out less than a meter. In effect, they are small delta wing to grafted onto the front of the normal wing. So this you can see here that this type of small wings are here. This you can see here. These are added in different, it is called leading edge extensions. Next is the leading edge cuff. The leading edge cuff are the fixed aerodynamic devices employed on the fixed wing aircraft to modify the airfoil used. They can be either factory installed or more commonly an aftermarket modification. In most cases, a leading edge cuff will droop the leading edge of the airfoil. This has the effect of causing the airflow to attach better to the upper surface of the wing at a higher angle of attack, thus lowering stall speed. This allows lower approach speed and shorter leading edge distances. Wing vertex generator, another lift producing device is wing vertex generator. In order to reduce the drag caused by supersonic flow over portion of the wing, small airfoils called vertex generators are installed perpendicular to the surface of the wing. They are mounted in complementary pairs. This causes the vertices being developed to aid one another, thus increasing the effect. On some aircraft, fences are installed on the wings and the ailerons. This gives more stability and control of the aircraft, reduces buffeting and reduces high speed stall characteristics. This wing vertex generators are shown here. This you can see here that some some grooves are here from here to here. This is an air is entering from here and it is expanding like this. So the kinetic energy is increased due to this area difference. So in the wing vertex, this you can see here, this is the wing here, and these are the VGs, Vertex generators. Air is moving from here, like this, and the velocity is increased here. Velocity increased. So this you can see here that it is like this. Shape is here, it is aerofoil shape here, and like this two things are attached and air will enter from here. This you can see here also a number of, it is fixed in the Boeing 777 wing vortex generators near the RA to R. Okay, so here this you can see this one, and this air will flow from here to here. Like this we are fixing, and they are generating the vortex. Each places they are generating the vortex, and this vortex are having more energy, so that it is pressing the against to the pressure gradient, and the stall is delayed, and the flow separation point is further pushed backward towards the trailing edge. So that is why it is producing the high lift, low drag, and they are the secondary devices for the aircraft. Next is illustrate the fly-by-wire control loss. So we have seen in my previous lecture also that the fly-by-wire were introduced in aircraft to reduce the pilot load, reduce the weight of the aircraft, to give the more reliability of the aircraft. It is redundancy of the aircraft is increased. The engine power requirement is reduced due to the low weight of the aircraft, and these are the very good benefit for this fly-by-wire. But what the control law the fly-by-wire follows? So here we have the three laws, 1, 2 and the 3. First law is the normal normal law. Basic control laws alongside conditional algorithms help to detect failure and to revert the systems to alternate law. Alternate law means what? The normal law means what? Basic control laws alongside conditional algorithm. So we have to put some algorithm, and it has to operate under this condition. In case, help to detect failure and to revert the system to, if it is able to detect some failure during operation, it will give to the alternate law. So what is the alternate law? This law basic controls laws without any additional handling. In this, it will handle in case of any further failure, it should be revert to the mechanical actuation. Next is the direct law. Direct law relation from control stick to the control surfaces. So this is a direct law. So here normal law. In this diagram, this normal law, you will see that most double failure, that is a computer, hydraulic and ailerons. Then it will goes to the alternate law. This alternate law will go directly if it is failed to the mechanical. If you see the next, here certain triple or the double undetected failure will go to the direct law, and from here direct law, if it is happening, it will go to the mechanical reversion. From here direct law, it can go to the crew intervenes, the pilot can intervene, and in this type of system, normal law, alternate law and the direct law are followed. These are the basic fly-by-wire control laws. These fly-by-wire control laws are applicable and applied for many aircraft, but here I am showing you one fly-by-wire in Airbus. So in Airbus, we have the 7 computers, 3 independent hydraulic power supply, electrical for most, and mechanical control the rudder. Most of the control are the electrically operated, but rudder is mechanically operated control. So here, for initially, here we have the 2 computers, 2, and here we have the 3. 2, 2 and 3. We have the 7 computers, 3 independent hydraulic power supply. So we have 3 independent green, yellow and the red, GYD. Okay, so green, Y and the red. 3 independent hydraulic power supply we have. Then we have some electrical electrical systems, and the last for the rudder we have the directly mechanical. It is a fourth order of your redundancy is obtained by fly-by-wire system on the Airbus 320. This is the Airbus 320 system. Next, for different primary flight control systems, we have the elevator control system, we have aileron control system, we have the rudder control systems. So, next is explain elevator control system. So, elevators are used for the nose pitching motion. Okay, just you can see here. This is the aircraft. Aircraft is flying like this. We have here the horizontal tail, and then we have the elevator. So how these elevators are working? An elevator is mounted on the back edge of the horizontal stabilizer. Just you can see it is back edge. They move up and down. These elevators can move up and can move down as per the pilot fixing or moving the control stick. It can be like this up, and this can be down. When the pilot pulls the stick backward, so if the pilot is putting stick backward like this, then what will happen? This elevator will go up. So if you want to back means nose up, elevator will go up, and vice versa. This makes the wing fly at a higher angle of attack, which generates more lift and the more drag. So if you want to make up or the down, it will also generate more lift, and also it will generate the more drag, and pitch moment is happening. So if it is like this, force will be generated. It will go like this, or it will go like. So if it is pulling backward, this will go up, nose will go up, and same thing happen in the opposite direction. So here I am showing the how the elevators are working, and these elevators, this you can see here. This is the top view, and these are the elevators are fixed here. If you want to make nose down, this elevator has to go down. Here it is a down. Elevator down, nose down, dive. So aircraft will start diving like this. If you want to make nose up, this is the nose down. So you have to put up. So what will happen in the up? So just I will discuss here first how this thing. Here is the center of gravity of this aircraft. This is the CG point, and you want to you have put down. Then air will go like this, and it will go like this. Air will go like this. So here angle of attack is increased. Additional lift of the tail will generate. This lift of the tail into this distance, it is called the moment of xt. So a moment of lt into xt, and this direction will be like this, nose down. This nose down action will be obtained by this way. If you take the next case here, this case here, it is up elevator. So what will happen? Air is entering here, and air is going like this. Air is moving like this. A lift force will act in this direction. It is LT, and here is the CG again. This distance is a moment of XT, LT. So here LT into XT. The moment is in which direction? In this direction. Okay. So it is like this. It is a nose up. So here it is shown the nose up. So this is the working principle of our elevator. Elevator is used in this way, and the flow I have shown, the aerodynamically how it is behaving, I have shown here. So now explain about aileron control system. So ailerons are mounted on trailing edge of each wing. So this I can show you here that this is the ailerons. Ailerons are here. Ailerons are here. They are on the trailing edge at the tip of the wing. Trailing edge at the tip of the wing. So they give more mileage and more arm this distance from here to here is high. If you are putting here, the distance will be reduced. So more size of ailerons are required. That is why elevator, rudder and ailerons are kept far away from the center of gravity of the aircraft to get the mileage of its moment arm. Ailerons are mounted on the trailing edge of each wing. They move in opposite directions. When the pilot moves the stick left, that you can see, this is the stick, and if he moves the left, then means it has to go down. So the right wing aileron will go down and the left wing will go up. So wherever which side pilot is putting the stick, that side will go up. A raised aileron reduces the lift on the upward ailerons and a lower one increases the lift. So this side will increase the lift. Centering the stick returns the aileron in the neutral, maintaining the bank angle. The plane will continue to turn until opposite aileron motion returns the bank angle to 0 to fly the straight. So if you put like this, it will be bank, then it will again come to center. It will start banking. Aircraft will fly in the same condition. Just you see, if you are banking, putting like this stick, aircraft is bank and it will continue banking like this. If you want to come again, you have to put other side. You have to put like this, then it will come like this and then it will be maintained. So in this way, ailerons are working. This diagram is shown here again for further explanation. The aileron down, right one up causes a roll to the right. So if you see this aileron up and this is the aileron down. So what will happen? Down will more lift and here is less lift. Moment will be like this. So it is shown like this. Opposite will happen in this left aileron up, right aileron down. So it will go in this direction. So the aileron matters and this is shown by the help of this diagram. Illustrate the rudder control system. These rudders are mounted on the back edge of the fin in the empennage. This you can see here. This is the empennage and this is the vertical fin. So mounted on the back edge of the fin in empennage. When the pilot pushes the left pedal by the feet, it has to operate. The rudder deflect left. So if it is pushing the left, it will go to the left. Pushing the right pedal causes the rudder to deflect right. So if it is right, it will go towards the right. Deflecting the rudder pushes the tail left and causes the nose to right. So if it is going left, then it will go and tail will go towards the right. Centering the rudder pedal returns the rudder to neutral and stops the yaw. Here it is shown here. This is the vertical tail. Vertical tail or fin. It is also called the fin. And here is the rudder here. So just you can see here that this rudder, it is turns towards the right. So if you turn towards the right, then a force will act in this direction and the nose is here, nose will also move in this direction. So in this way, the rudder is behaving and this rudder is applied in this way. Now the discussion on aircraft motion and the control. This we can see here that we have the axis, motion stabilized by control and the pilot control of what control is to be used. So first one is the longitudinal. In this longitudinal means nose. This is the longitudinal axis. So this rolling will happen either this side or this side. And in this ailerons, these are the ailerons. These ailerons to be used as per the requirement. Yoke, twist left or the, so there is a yoke, so you have to twist left or the right. Lateral means pitch. This horizontal stabilizers are here. This you can see here. This is the horizontal stabilizer here. These elevators are here. These elevators makes the yoke forward or the rear. if you make yoke forward, it will go down. If you want to yoke upward, it will go upward. Next is the vertical or the yaw. Vertical stabilizers are here. This you can see. This is the vertical stabilizer here, and this is the rudder here. So the rudders are used to do this, and this is operated by the feet of the pilot. The pedals are there. By the help of the feet, it will happen. And if you are pushing the left pedal, your rudder will go towards the left and your nose will go towards the left. So it is directly related with the system. So it is the discussion on the aircraft motion and the control of the aircraft. Now, demonstrate the secondary flight controls. We have the elevator trim tab system and the rudder trim tab system. They are the secondary. So this elevator trim tab, these trim tabs are fitted on the elevator. Just you can see here, this is the elevator and a small part is here, and it can balance. It can make the system very easy and free of load. Elevator trim balances the control force necessary to maintain the aerodynamic downforce on the tail. When aircraft is flying, a lot of trim could be required to maintain the desired angle of attack. This mainly applies to slow flight, where maintaining a nose up attitude requires a lot of trim. An important design parameters for aircraft is the stability of the aircraft when trimmed for level flight. Any disturbances such as gust or turbulence will be damped over a short period of time, and the aircraft will return to its level flight trimmed airspeed. Elevator illustration in action. Just you can see here that elevator is here and this is the trim tab. So if the elevator is going down, trim will go up, tab up, elevator down, and here elevator up, tab down. So the forces are balanced. So in this, forces are balanced and aircraft is flown hand free by the pilot. So that is the advantage of this trim tab. Explain the rudder trim system used in airplane. Trim doesn't only apply to elevator, as there is also trim for the rudder and the aileron. The use of this to counter the effect of slipstream or to counter the effect of the center of gravity being to one side. This can be caused by a larger weight on the one side of the aircraft compared to the other, such as when one fuel tank has a lot or more fuel in it than the other, or when there are heavier people on the one side of the aircraft than the other. That time these rudder trim tabs are used. Here I can show the rudder trim tab here. So this is the rudder and these are the rudder trim tabs. Here is the elevator and this is the elevator trim tabs. So they are also used in opposite direction. If the rudder is moving in this direction, trim tab will go in opposite direction. So that is the working principle of this. So here I have the references: Moyer I and the Seabridge aircraft systems, mechanical, electrical and avionic systems, Professional Engineering Publishing Limited, London, and Bury St Edmund, UK, ISBN this number. Next is the Moyer I and the Seabridge, Design and Development of Aircraft Systems and Introduction, AIA Education Series. And also I have this slides here which is used here. Any questions you are welcome to ask. I am always available for any queries. It will be my honor to reply you, and please be in contact with me. My email is ydwivedhi@gmail.com. Hope my lecture you have liked very much. I am ending my discourse here, and thank you very much for joining. Wish you all the best, and thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.